The should be question one of the exam that our friends wrote. This one comes from Cob Douglas production function. In short, it comes from optimization. So there's a topic in economics called optimization, which just looks at how firms can maximize their profit, how consumers can minimize how producers can minimize losses and all those things. So remember, the aim of a firm is to maximize profit and minimize the losses or minimize the cost, and the aim of a consumer is to maximize their utility. So we use optimization to find the optimal values. Let's say it's a firm, so we use the concept of optimization to find the optimal amount of output that should be produced for this firm to maximize its profit, or maybe the optimal amount of capital and labor that this firm needs to employ for it to minimize the losses. So that's the application of optimization. So the question is saying, suppose a firm produces a single output using labor and capital as inputs. So remember, this firm is into production. For it to produce a given amount of output, it needs the factors of production. And in this case, those factors of production are capital and labor. Then the firm, of course, has to use some form of a production function. Now, what is a production function? So production function is just a relationship between inputs and output. How many units of inputs do you need for you to produce a given a certain level of output? So that relationship between the inputs and the output is captured by the production function. So in this case, we're assuming that the production function of this firm is a Cob Douglas production function. Now, a Cob Douglas production function looks like this. So Q is equal to, so in this case, we are saying that output is a function of capital and labor. So that's the Q is equal to FKL. So output Q is a function of capital and labor. And this is equal to A K. In this case, it's AL. So it's AL to the power alpha, then capital to the power beta. In short, that is the general form of a Cob Douglas production function. So a Cob Douglas production function looks like that. A, L raised to the power alpha, then I've got capital raised to the power beta. All right. Now, well, first thing first, we should first understand what this thing is all about. So in the production function there, the A is the measure of technology. Okay, so the A is the measure of technology, then L is the labor units, of course. So L is labor units. Then the alpha is the the contribution. So the alpha there is the contribution of labor to total output. Okay, and then of course the K is the capital units. So this is the number of capital units that we are employing, and then the beta is the contribution of capital to total output. Contribution of capital to total output. So that's the breakdown of our Cob Douglas production function. All right, so the A is the measure of technology. So the A there just measures the productivity, or how productive are these two factors of production. So the A there is just the technology. It measures the impact of technology. Then L is the labor units, of course. And then that exponent, the alpha, is a measure of the contribution of labor to total output. Yes, sir. Okay, but are you still able to see my screen? Oh, great. Okay, fine. So I was saying that, so I have this breakdown of our Cob Douglas function. So the A is the measure of technology, the impact of technology, yeah, in our production. Yeah, great. And then the L, that L there is the measure of, or it's just the labor units, just the units of labor. How many units of labor are we employing as a firm? Okay. And then the alpha, the power of labor, is what we call the contribution factor of labor. So it measures the contribution of labor to total output. Okay, so the alpha measures the contribution of labor to total output. Then the K is the capital units, the number of capital units that we are employing. Yeah, and then the beta there is the contribution of capital to total output. So that is the breakdown of the Cob Douglas production function. All right. So let me just get the feedback if so far we are still together. No, perfect. Madam Tembo, are you there? Okay, so far oh, great. All right. Yeah, so now look. Yeah, we know that the target of the firm is to produce a certain amount of output, yeah? But then what we also know is that for this firm to produce this amount of output, it needs, some factors of production. You need capital, you also need labor, yeah? And you don't just get capital and labor for free. You have to pay, right? So now we find that in as much as the firm wants to maximize its output, it has to minimize the losses. It has to minimize the cost. Yeah? So therefore, the total cost comes from the cost of inputs. Okay? So the total cost is the cost of inputs, which is the cost of labor plus cost of capital. Okay, since in this case we only have two factors of production. So the total cost therefore comes from two. It's the cost of labor and the cost of capital. Putting them together, then you have your total cost. Right. Now in this case, let's go back to the question. The question is saying the firm faces the budget constraint. Yeah? So the firm faces a certain budget constraint. And what we know also is that, so let's focus on that portion there, which is saying that a firm has a Cob Douglas production function with alpha is equal to 0.6. So let's just organize our formula. So remember, so we'll come back to the cost. I just want to move in order. So let's go back to the Cob Douglas function. Yeah, so you've said that our Q is equal to A K to the power alpha and then L to the power beta, and then the statement is saying that a firm has a Cob Douglas production function with alpha is equal to 0.6 there. So alpha is equal to 0.6 and then beta is equal to 0.4. Okay, we've also been told that the total factor productivity is 100. So the A, which is the factor productivity or technology, is fixed 100. So our A is 100. Yeah? Great. And then we are also being told that the wage rate is 10 kwacha per unit of labor. So the wage rate, W, the wage rate is 10 kwacha per unit of labor. And the rental, yes sir, yes sir. Oh, upwards. Oh, yeah, you're right. I usually it's supposed to be AL. You're right. ALK, like that. Great. Great. That's okay? Oh, great. Yeah, great. Okay, so let's go back. Yeah, so that's our production function there. Alpha is 0.6, our beta is 0.4, our factor productivity or technology is 100. Yeah, then the wage rate is 10, and then the statement is saying and the rental rate of capital is 20 per unit of capital. So the rental rate of capital R is 20 kwacha per unit of capital. Now let me explain what's going on. What's going on is that, yes, this firm wants to maximize output, yeah, but you cannot just maximize output minus dealing with the cost side. And we've said that the total cost is supposed to be the cost of labor plus the cost of capital. So therefore the total cost will be equal to the units of labor that we are hiring, yeah, multiplied by the wage rate per each unit of labor that we're hiring. You see that, huh? So it's a number of people that we are hiring. Let's say 2 security guards. Each will be given a wage. So therefore the total cost of labor is the number of security guards we are going to hire multiplied by the wage that each security guard will be getting. You see that, huh? So that is the total cost of labor. Plus, now we have to add the cost of capital. And the cost of capital will be the number of capital units that we are hiring multiplied by the rent that we'll be paying for each unit of capital that we're going to hire. So this is the general formula of the total cost function. Right? So now let's put it together. So our total cost will be equal to, we don't know the number of units of labor that we want, but we know the wage rate. The wage rate is 10. So this is the same thing as saying 10 multiplied by L, where 10 is the amount of money that each labor unit is expected to be receiving, yeah, times L, where L is the actual number of labor units that we want to be hiring. So that is the cost of labor plus the K we don't know. So we don't know what K is, but at least we know that each unit of capital should be receiving a 20 kwacha. So now this is the total cost function for our question at hand. So the total cost therefore is 10L plus 20K. 10L plus the 20K. So that is the total cost function. Okay. How about the Cob Douglas itself? Let's put it together. We know that Q is A L to the power alpha, then K to the power beta. So we know that the A has been given as 100 there in the question, the statement. So it means that where there is A, we're going to put 100. We put our L. Alpha has been defined to be 0.6. So you put our 0.6 there. Then you put K to the power 0.4. So now we've got the two pieces that we needed. Yeah? We've got the two pieces that we needed. The cost function and the Cob Douglas production function itself. So this is how we use this information to come up with these functions. Okay, so let me just get the feedback up to this point. Yeah. Madam Temple, how is it so far? Oh, great. Boss, how is it going so far? Great. All right, perfect. So now the question is saying that can we calculate the firm's production function and determine the level of output Q it can produce given the inputs of labor and capital? 10 marks there. So first thing first, can we calculate the firm's production function. And we have already done that, because now we know that our production function is that. Okay, so at least we have the firm's production function. But the other part of the question is saying that after calculating for the firm's production function, can you find the total amount of output that the firm can produce, given labor and capital units? Now here is where the real gymnastics starts. Okay, so now for us to find this level of output, we have to use what is called the Lagrangian function. Okay, so we need to use what is called the Lagrangian function. Okay, now how does a Lagrangian function look like? Well, it's simple. A Lagrangian function looks like this. So you're going to have what is called the objective function. So you're going to put the objective function here, and then to this objective function you're going to add lambda, and lambda looks like something like that. Then you're going to multiply this Lagrange by the inverse cost function. Just like that, simple. Okay, so I've got the objective function plus the cost function there. Right, great. Now, what is the objective function? So the objective function is our Cob Douglas function. So please, don't confuse the two. The Cob Douglas production function, is this function Q is equal to 100 L to the power 0.6 K to the power 0.4. That is the Cob Douglas function. But now the method of calculating for output is what we call the Lagrangian function. Alright, so don't confuse the two. Okay, so we are saying that this objective function will look like that. So we're going to let's call this we can give it a letter, let's say H. So we're saying that H is equal to the objective function plus lambda multiplied by the cost function. So that is a Lagrangian function. Can we come up with this function? Yes, we can, because now we know that this thing, the Cob Douglas function itself, is the objective function. So therefore the objective function is just 100 L to the power 0.6 K to the power 0.4. That is the objective function. So to this objective function, we're going to add lambda, open brackets. Now, how do we put the cost function? Remember that the cost function is this function here. This one there, total cost is equal to 10L plus 20K. That is the cost function. Maybe we didn't finish reading something. I think there's something that we didn't pay attention to. There's 1,000 somewhere. Yeah. So the statement is saying the firm's total budget is 1,000. Okay, so we didn't consider the 1,000. So where do we put the 1,000? Well, what we know is that the total cost, this total cost here, let me put it in red, that total cost there. Now we know that the total budget for the inputs is 1,000. Yeah? Which means that after hiring some units of labor and some units of capital, we should spend 1,000 kwacha. That is what it means. We should spend 1,000 kwacha. You see that, right? So therefore, this means that the total cost is 1,000. So 1,000 is equal to 10L plus 20K, like that. Okay, so that is our cost function there. So now going back to our Lagrange, we are saying that Lagrange is equal to the objective function plus lambda multiplied by the inverse cost function. And now Our objective function is this one, the Cob Douglas itself, the 100 L to the power 0.6 K to the power 0.4. Then to this we're going to add lambda plus open brackets. Now, what is this cost function? The cost function, we know that it's this one, right? 1000 is equal to 10L plus 20K, right? But when putting it here, we are going to start with the 1000, yes? So put the 1000, and then we're going to get everything on the right hand side to the left hand side. You see that, right? So we're going to get the 10L and take it to the left hand side. The 20K will take it to the left hand side. In short, everything on the right should cross the equal sign and go to the left hand side when putting it in the Lagrange there. So the 10L will become minus 10L after crossing the equal sign. Then the 20K will become minus 20K after crossing the equal sign. Okay, I hope that's okay. Yeah, I pray that that's fine. Yeah, Madam Tembo, kindly confirm if this is okay. Okay. Oh, great. Perfect. Now, let's do the gymnastics now. So now, after putting up the Cob Douglas function like this, step number 1, open the brackets. Okay, so for me, I love notes because these notes help when they really help when revising alone. So from here, step number 1, open the brackets. Which brackets? These brackets here. Those brackets there. Remember, we said lambda multiplied by. You see, so now we have to open those brackets there. So our h will become 100 L to the power 0.6, then k to the power 0.4, then plus. Now we're going to start multiplying this lambda times 1000. That will give us 1000 lambda, right? Then we'll multiply the same lambda times minus 10L, which will become minus 10 lambda L. Then the same lambda, can we multiply it with the minus 20K, which will become minus 20 lambda K. You see that, huh? So we've opened the brackets. The second step is to get what we'll call partial derivatives. So get the partial derivatives. Okay, so can you get the partial derivatives? Now, what are partial derivatives? This is now the concept of calculus. Okay, differentiation, calculus, differentiation. So just a reminder, partial derivatives just involves differentiating a given function with respect to one factor while keeping all other factors constant. So in this case, let's say we want to get the partial with respect to capital, we'll differentiate the function with respect to capital and keep labor constant. And the opposite is also true for the other factor. Okay, so let's get the partial derivatives. Or one more thing, how do we differentiate? Yeah, so if we have a function, let's say y is equal to a x to the power n, to get the dy dx, dy over dx, what we do is we get that power there, the n, and multiply it with the a, where the a is this one, right? Then we're also going to multiply that by the x, and then from the power we're going to subtract a 1. So dy dx will just be nax to the power n minus 1. Practically, let's say our y is, let's say, 4x to the power 2, and then we want to get the dy dx. We want to differentiate this. How do we differentiate? We know that we'll get that 2 multiplied by the 4, yeah, then we're also going to multiply this whole thing by x, yeah, and then from the power, which is the 2, we're going to subtract a 1, meaning that our answer will just be 2 times 4, 8, multiplied by x to the power 1, because 2 minus 1 is a 1. So that is how we differentiate. So we're just going to borrow this same concept and apply it here. Okay, so that was just a reminder on differentiation. Okay, great. So with that information, let's try to borrow the concept and apply it here. Let's get the partial derivatives. So first thing first, we're going to get the partial derivative of this function. So it's the partial of h with respect to any. Let's start with labor. Okay, so now with respect to labor, check this out. Labor is featuring here because there's labor there, and it's also featuring there. Yeah, so since we are talking about partial derivatives, we are going to only differentiate those terms containing L, only those terms where L is featuring. And those terms without L, we assume they do not exist. We assume, in short, we're just going to keep them constant. So that's the concept of partial derivatives. We only differentiate that term containing that particular variable under consideration while keeping all other expressions or all other terms constant. So that's the concept of partial derivatives, right? Great. Okay. So uzafaka mabando mufoni woyo bando inasida mailo unsokoneza yenda sorry, my friend was just trying to disturb me. Okay, great. Let's move. Yeah, so let's do the partials now. Yeah, so now let's start with the first term there. We want to differentiate this term with respect to labor, and this labor is raised to a power there 0.6. So how do we do this? That power there, the 0.6, should drop. Okay, so it will be 0.6 multiplied by 100. This thing multiplied by labor. Yeah, but now since we are differentiating with respect to labor, get me right on this one. Since we are differentiating with respect to labor, from the power of labor, yeah, from the power of labor, which is a 0.6, right? From the 0.6, we are going to subtract a 1. You see that, right? And then write capital to the power 0.4 just the way it is. Why haven't we, subtracted a 1 from 0.4? It's because we are not differentiating with respect to capital. We are differentiating with respect to labor. And since we are differentiating with respect to labor, we need to subtract a 1 from the power of labor. The power of capital will be as it is, 0.4. It will remain untouched and undisturbed. Why? Because we're using the concept of partial derivatives. You see that, right? Great. Then where is labor again? So labor is also present there, which means that we have to differentiate that term minus 10 lambda L with respect to labor. Yeah, so this will become minus, which is that negative there. Hi, someone's mic is on. No, it's okay. Okay, great. Yeah. So we put a minus there. Yeah, then we write our 10. Okay, or even before we do that, check this labor there is raised to a power. There's a power there, though it's not there, but there's a power. It's not 0, it's 1. Okay, so even if we know that this is like this, minus 10, let me put it in red, it's minus 10 lambda L, right? So this labor is raised to some power. So there's a power there which is a 1, even if it's not shown there, but there is a 1. Okay, you see that? So we have got a 1 there. So now remember what it is, as long as we're differentiating with respect to this particular variable, the power of that variable should drop. Yeah, so this is more like saying a 1 here, open brackets, we put a 10 inside, then we multiply this with lambda, of course, then we multiply this again by L. But check this out. We are saying that we are differentiating with respect to labor, right? And what we do, we remove a 1 from the power. And in this case, the power of labor was 1. So therefore, now the power will become 1 minus 1. You see that, huh? Great. So from here, we just have to simplify this. Okay. So far, how is it? So far, how is this step? This is the most confusing step. Let me get some feedback. Where on labor 1 minus 1 there. Oh, yeah, we'll simplify that. Madam Tempo, how is it on your end? Oh, great. Okay, great, perfect. Yeah. So this will now be, let's simplify. So I assume you have calculators where you are, because you can't deal with this course without a calculator. So we start now. You can punch 0.6 times 100. This will just give you a 60, because it's more like we're saying 60% of 100 is 60, right? Yeah. Then to this, we're going to multiply with this L to the power that. So it's L to the power. Now check, the power is 0.6 minus 1. When you go in the calculator and punch 0.6 minus 1, you're going to get negative 0.4. Then you put your capital to the power 0.4. Yeah. Then minus. Let's deal with this part. We have minus 10. Okay, so minus 10 times lambda. Now look at labor. Our labor is raised to the power 1 minus 1. So look at this now. L to the power 0 is just a 1. So please write this. Anything raised to power 0, the answer is a 1. So anything raised to power 0 is equal to 1. Therefore, L to the power 1 minus 1 is the same thing as saying L to the power 0, and L to the power 0 is a 1. Even if it's 1 billion to the power 0, the answer is a 1. Okay? So, this is going to be, we're just going to equate our whole function here to 0. So, this is the derivative or the partial derivative with respect to labor. Just labor. But we also have to get the partial derivative with respect to capital. So if you have understood this, how we do for labor, it will be, you just borrow the same concept and use it for partial derivative with respect to capital. Right, great. Okay, fine. Let's get the derivative with respect to capital. So where is capital featuring? Capital is featuring in the first part because it's there, and it's also featuring in the last part there. Okay, great. Let's do that. So for the first part, our capital is raised to the power 0.4. So this will be 0.4. The 0.4 will drop. Remember differentiating. So it will drop. We're going to multiply this by 100. Yeah. Then we're going to put capital. Oh, sorry. We're going to put the labor to the power 0.6. So please get me right. This time around, we are differentiating with respect to capital. And since we are differentiating with respect to capital, labor will be unaffected. It will be as it's supposed to be. It will be, you remember that assumption of ceteris paribus, right? You only focus at one thing, keeping everything else constant. So we are not differentiating with respect to labor. Therefore, labor will be as it is, just labor to the power 0.6 unaffected. Then, let's put capital. And remember now, since we're differentiating with respect to capital, the power of capital will be the 0.4 minus 1. Okay? That's with the first part. The last part there, which is negative 20 lambda k, we know that we're differentiating with respect to capital, right? Yeah? And that capital is raised to a power 1. So that will be, so we're going to put a minus, which is that negative there. We're going to put it here. We write our, so we're saying 1 times, we put a 20 times lambda times k. But our capital is raised to the power 1. We subtract a 1 from that one. Okay? Then what do we do next? Simplification. We have to simplify, yeah? So 0.4 times 100 is just a 40. So 40 L to the power 0.6. We've got capital to the power. Now 0.4 minus 1, we're going to get minus 0.6. Then I've got minus 20 lambda. This is also equal to 0. You get, ka? Now from this, always remember that. So first thing, get the derivative with respect to labor. Second thing, get the derivative with respect to capital. Thirdly, get the derivative with respect to lambda. Remember, there's this term, the lambda term. There's this term. So there's lambda there, and then there's also a lambda there. So that term should also be differentiated. Okay, don't feel lazy. Okay, so change in h, you change in lambda. Now with this one, don't worry. Why? Because the moment you differentiate, you always get this term in the brackets here. Remember there when we are putting up the Cob Douglas function, the Lagrange, right? We said that it's objective function plus lambda multiplied by the cost. So when you differentiate with respect to lambda, you always get that term in the brackets there. Okay, so you always get that term in the brackets, which is 1000 minus 10L minus 20K. So the derivative of h with respect to lambda will just be 1000 minus 10L minus 20K. You see that, huh? So those three steps, don't forget them. The derivative with respect to L, the derivative with respect to capital, the derivative with respect to lambda. Don't forget those ones. Okay. So that's the first step, right? Oh, second step, actually getting the partial derivatives. Third step is to equate. To make lambda the subject of the formula. So make lambda the subject of the formula. But here I mean from equation 1 and equation 2. So let's call, let me put it in red. Okay, let me first clear this part a little bit. It's a bit messy there. Yeah, so let's call this equation the simplified partial derivative with respect to labor. Let's call that equation 1. Yeah, and let's call this equation the simplified partial derivative with respect to k. Let's call this equation 2. Yeah, so what I mean is in step number 3, from these two equations, right, make lambda the subject of the formula. So make lambda the subject of the formula from equation 1 and equation 2. So that's the step number 3. Okay, now look, we said that there in equation number 1 we have 60L to the power minus 0.4, then capital to the power 0.4 less 10 lambda is equal to 0. Yeah, in equation 2 we have 40L to the power 0.6, k to the power minus 0.6 minus 20 lambda is equal to 0. All right, so we are saying that from these two equations, can we make lambda the subject of the formula? Now from equation 1 there, we know that here we're just using algebra. You see that, huh? So what we're going to do is we're going to get this minus 10 lambda and take it to the other side. Remember, our target now is to make lambda the subject of the formula. So therefore from equation 1, this will be 60L to the power minus 0.4 capital to the power 0.4 is equal to 10 lambda. You see that, huh? Then divide throughout by 10, so that you can just, in short, isolate lambda, let lambda be alone. Great, huh? So we are dividing here by 10, even this side by 10. So it will cancel on the right, 10, 10 will go. So there we've got lambda is equal to, now 10 into 60 is a 6, right? Yeah. So it's 6 L negative 0.4 capital 0.4. So that's the first lambda there. We call that lambda 1. So lambda 1 is the 6L to the power minus 0.4 K to the power 0.4. That is from equation 1. Oh, okay. Not a problem. Not a problem. Not a problem. So, we have two equations. Remember, we made equation 1 and equation 2 from the partial derivatives, yeah? So, what we're saying is that from the first partial derivative, can we make lambda the subject of formula? Yeah? So, our equation 1 is this one. 60L to the power 0.4 K to the power 0.4 minus 10 lambda is equal to 0. That is our equation 1. Yeah? Great, yeah? Then, what we're saying is that from that equation, can we make lambda the subject of the formula? So, we are going to say 60L to the power minus 0.4 K to the power 0.4 is equal to 10 lambda. In short, can we get the minus 10 lambda? Can we take this guy to the right hand side? So we know that the moment something crosses the equal sign, the sign changes, right? So if it was initially negative, it becomes a positive. If it was a positive, it becomes negative. Yeah, great. So this now will be like this, and then we're going to divide by 10 here and also by 10 there. So on the right, we've got 10 on top, 10 down. We'll cancel those. You get that? So this is equal to, now on the left we can divide the 6 and the 10. So 10 into 60 is 6 times. So I've got 6 L minus 0.4 capital 0.4, like that. So that this is our first lambda from equation 1. How is that, sir? Okay. Madam, how is it? Great. Oh, great. I see. Yeah. Then again from equation 2, we do the same. From equation 2, that one, we do the same. So the equation is 40L 0.6 K minus 0.6. As usual, can we get the minus 20 lambda to the other side? So this becomes is equal to 20 lambda. Then we divide. We divide like that. Okay, so we cancel on the right. We've got lambda 2 is equal to 20 into 40, 2 times. Then we've got L to the power 0.6 capital minus 0.6, like that. Step number 4, equate. So equate the two lambdas. So can we equate the two lambdas? Remember, we've got lambda 1 this one, we've got lambda 2 that one. Yeah, can we equate them? Yes, we can. So this means that we have to do lambda 1 should equal lambda 2. Okay, like that. So this will be 6L minus 0.4 K positive 0.4 should be equal to 2L to the power 0.6 K minus 0.6. So what have we done? We've just equated the two lambdas. You see, we just equated the two lambdas. Papa. Okay. Next thing is to, so let me say you equate the two lambdas. So let's add one more thing and say and apply the laws of indices. Okay, so you equate the two lambdas and apply the laws of indices. Now look at this, huh? This is simple. Why? Because on the left hand side, our labor is raised to a negative power. On the right hand side, our capital is raised to a negative power. You see that, okay? So now, how do we do this? How do we handle such a case? Well, we can, so this L, since our L here is raised to the power minus 0.4, right? This is the same thing as saying 1 over L to the power positive 0.4. In short, we just find the inverse of that term with a negative power. Okay, so that is that part there, the law of indices. Yeah, so this on the left it will be 6, right? Capital to the power 0.4 over labor to the power 0.4, like that. You see that, huh? So this is equal to, we do the same on the right hand side. So in short, all those with positive powers, they will remain on top. Those with negative powers will become denominators. You get, I believe that's fine. So this will be 2L 0.6 on the right divided by capital to the power 0.6, just like that. Okay, so we know that from here we cross multiply. Okay, so from here cross multiply. Okay, cross multiply. So we do like that. So the labor here will multiply by the 2L 0.6, huh? This comma capital to the power 0.6 will multiply by 6 capital 0.4. Right. Let's start with this labor multiplying by that with that side there. Okay, so that will be 2L 0.6 multiplied by L 0.4 is equal to the capital now with the other capital there. Okay, so that will be 6 capital to the power 0.4 multiplied by capital to the power 0.6. This is just cross multiplication. Okay, great, huh? Now look at this, huh? On the left hand side we have got labor multiplying with labor. So write this, let me just say under multiplication, so multiplication, if the base is the same, comma, maintain the base, so maintain the base and add the powers, so this comma 1, very important, this comma 1. So on the left hand side we're going to have 2, but look, we are multiplying L to the power 0.6 multiplied by L to the power 0.4. So what we're saying is that since the base is the same, L, labor, right? We'll write the 2, then maintain the base, which is the labor, and add the powers. So it will be 0.6 plus 0.4. We do the same on the right hand side. 6, we maintain the capital, we add the 0.4 plus the 0.6, like that. So that on the left we're going to have 2L. Why? Because 0.6 plus 0.4, the answer is 1. On the right hand side we're going to have 6K. Okay, then from here now, step number anyway, let me just write it as a comma hint. From here, choose. Okay, so make either, so from here make either L or capital the subject. The choice is yours. Okay, like that. Okay, so let's choose whichever. Let's make labor the subject of the formula. How can we make labor the subject of the formula? So let's say let me say make, in this case we are making labor. Okay, so let me say making labor the subject. So making labor the subject, we know that you have to divide. So divide both sides by 2. Yeah, So that since I've got 2L is equal to 6K, when we divide here by 2 and also outside by 2, we'll cancel on the left the 2's, then our L is going to be 3K. Why? Because 2 into 6, 3 times. Okay. Then now, step number 5. Replace. Okay. Replace or substitute. Substitute L is equal to 3K into the cost function. Okay. Into the cost function. Like that. Okay. So how is it this far? Is it making sense? Is it helping? Oh, great, great. Madam, how is it? Oh, great. Great. Oh, that's fine. That's really good. Great. I see. Okay. Perfect. So yeah, let's do the substitution now. Remember, we said that total cost is equal to 10L plus 20K, right? And then we said that 10L plus 20K should be equal to 1,000 because 1,000 was the budget for the inputs, right? Yeah. So now the goodness is we know what to put here where there is L. Why? Because here we say that L is equal to 3K. You see that, right? So this is the same thing as saying 10 open brackets where there is L we should put 3K. Then plus 20K. This should be equal to 1,000. So 10 times 3K, this will give us 30K. Then plus 20K. This is equal to 1,000. Yeah? 30 plus 20 is a 50. So 50K is equal to 1,000. Yeah? Then divide both sides by 50. Even here by 50 again, like that. So you cancel on the left. We are going to remain with K is equal to 20, right? So therefore, the optimum level of capital is 20 units. Great, right? So now at least we know that for this firm to maximize its profit, it has to produce it has to employ 20 units of capital. Yeah? How about labor? So to find labor units, comma, replace K is equal to 20 into the function for labor, which is L is equal to 3K. The one we defined that labor is equal to 3 times K. Yeah? So therefore, our L will just be 3K, which is 3 times 20. Therefore, L is 60 units. 60 units like that. So that is how we find the units of labor and capital. So therefore, for this firm to maximize its output, it has to hire 20 units of capital and 60 units of labor. Yeah, great. Yeah, then the question is saying, remember the question, huh? The question was actually saying, can you find the level of output? That is what the question was saying. Can you find the level of output? That is very simple. Why? Because so to find the level of output, yeah, substitute K is equal to 20 and L is equal to 60 into the Cob Douglas function. Okay, into the Cob Douglas function. into the Cob Douglas function like that. But remember that our Cob Douglas function was 100 L to the power 0.6 capital to the power 0.4, yeah? So now we know that the total amount of output that this firm can produce is going to be equal to 100. Where there's L, we know that L is 60. We'll raise this to the power 0.6. Where there's K, we know that K is 20. We raise that to 0.4. Then just go on the calculator and punch. So 100, open bracket, 60. I'm raising this to power 0.6, yeah? I'm multiplying that with 20 raised to power 0.4. So this is giving me something like Q is equal to 3866.36. If that's correct to 2 decimal places, yeah, it will be this. So that's the total amount of output that this system can produce. In short, that is what's supposed to be done there on question A. So you're just finding, you're just doing this. Sir, how is it? Fair enough? But you know, when you look at the marks, it's worth it. Yeah, so you know, with such questions, such questions you just have to, it's a must you do them, because they'll give you a lot of marks. You see, that's 10 marks. That's 10 marks. That's 10 marks. Okay, let's do B quickly. Determine the optimal combination of labor and capital that the firm should employ to maximize its output subject to their budget constant. But you see where the easy part is at the moment of hammered A, B is simple, because B is just saying determine the optimal combination of labor and capital that the firm should employ to maximize its output subject to the budget constraint. We already have the values. We've already found the optimal combination of labor and capital, because labor should be, did we say 60 units, and then capital 20 units? So what you do is this. For here, the question is saying determine the optimal combination of labor and the capital. The optimal combination of labor and the capital is just the inputs that you need. How many units of labor do you need? And also at the same time, how many units of capital do you need? So in short, what we have done so far covers for question A and question B. Because question A was just asking for output. Calculate the firm's production function, first part, and determine the level of output it can produce given the input of labor and capital. So we have calculated the production function, which we said is where is that part? Here, where we said the production function should take that form. So that's for the first part. Then what we have done, all these steps here are catering for both A and B. Then to find the answer for B, remember for A, because A was just asking us to find the actual amount that we can produce, and we said it's 3,000 something. And then B now is saying, well, can you give me the values of capital and labor? So you just say, as shown above, the optimal amount or the optimal combination of capital and labor is 20. So what you do is, for B, you just say you write the optimal combination should be, then you do this. You have got 20 and L, where 20 and what, and 60, right? Where the 20 is for capital, comma, the 60 is for labor, like that. Okay, so in short, whatever we have done here carries a total of 20 marks. But for you to earn the 20 marks, you have to show each and every step. So that even as you are making a reference on B to say, as shown on the calculations for A, you know that what you've done is the correct thing. You see that, right? Okay, so yeah, that's what we do there. It's not even that difficult. Oh, you haven't got it? Okay, great. So question B is asking us to get there to determine the optimal combination, right? The optimal combination of capital and labor. How many units do you need for capital and labor? And we've already calculated that we need 20 units of capital and 60 units of labor. So for B, you're just writing the optimal combination of capital and labor should be 20 units of capital and 60 units of labor. Okay, so for when we are solving, we have solved for 2060 because we needed those to find we needed the 20 and the 30 to put in the production function for us to find the total output, right? But for B is just asking us to find or to state or to find the actual amount of capital and labor that we need, which we have already calculated for. We have the values. Capital is 20, labor is 60. So on B there we just put the values. The optimal combination of capital and labor is 20 units of capital and 60 units of 60 units of labor and 20 units of capital, as shown above, or as calculated above. Is that okay, madam? Yeah. Sir, how is it? Perfect. Okay, let me see. My PC is becoming a bit slow. Okay, yeah. The free production region, the ISO can't correspond to the optimal level 1. 10 marks just like that, yes. But of course, remember what I've said, it's dependent on what you do on A. If your calculations are wrong on A, it's obvious that the B conclusion also be wrong. So you have to pay attention to detail. So the long process pays off at the end of the day. Yeah. Okay. Isoquant. So question C is saying show graphically the feasible production region, the isoquant corresponding to the optimal level and the budget constraint. Oh, fine. This is simple again. So for C, right? Why is this thing misbehaving now? Yeah, so for C is saying show graphically the feasible production region, yeah, the isoquant corresponding to the optimal output level and the budget constraint. So what it is this, you're just doing this command graph. So here we are going to put capital, they are going to put labor. What we know is that this is what we call the budget line, this comma 1, or the budget constraint, sorry. Okay, so we're just going to put a comma line there like that, like that. And then we know that according to our calculations, we said, I've forgotten the figures, labor 30, 60 and 20. Which one is 20? Which one is 30? Okay, great. Okay, so capital is 20, labor is 60. Fine. capital is 20, right? Then labor is 60. So you do like this. So capital is 20, labor is 60. So let me explain this. Anything within or below the line, below this line that we've drawn, anything, in short, this region in red here is what we call the feasible region. Okay, the feasible region. We can produce any amount of output within this shaded region here. Okay, and the optimal combination is at that point where the isoquant, so the isoquant is this comma curve. Okay, isoquant like that. So at that particular point A, okay, so let me write this. We say at point A, so at A, comma, the slope of the isoquant, which is called the marginal rate of technical substitution. So marginal rate of technical, marginal rate of technical substitution. So at point A there, the slope of the isoquant, which is the marginal rate of technical substitution, is equal to the slope of the coastline. Okay, now what do we mean? What it means is that, remember, first thing first, this shaded region is the feasible region. We can produce anything, we can produce any level of output as long as that output falls within the shaded region, right? Then the best combination of capital and labor is at point A, where we've got 20 units of capital and 60 units of labor. And at that particular point at point A, the slope of the isoquant, and the isoquant is this comma curve. Maybe let me also define the isoquant. So an isoquant the isoquant is a curve or a locus of points showing showing various combinations of capital and labor that can produce a fixed, that can produce the same level of output. So that's the definition of an isoquant. So an isoquant is just a locus of points or a curve that shows the various combinations of two factors of production. So in this case, various combinations of capital and labor that can produce the same level of output. So now, at the optimal point, the isoquant is tangent. So to be tangent is to touch a curve at one particular point. So at the optimal point, the isoquant is tangent to the coastline. What does that mean? It means that at that particular point, the slope of the isoquant is equal to the slope of the coastline. Okay? So we have shown the feasible region, which is the shaded region. We've also shown the optimal combination of capital and labor. And we've also shown the isoquant and the optimal point. At that particular point where the isocost is equal to the slope of the isocost is equal to the slope of the isoquant. So don't confuse the two. The isocost is the line, this line that starts from A or there to K there. The isoquant is this curve now, this curve that shows the various combinations of capital and labor that can be used to produce the same amount of output. Okay, how is this concept? Oh, great, not a problem. Not a problem. Yeah, so the question is saying, show graphically the feasible production region, which we have shown that it's this shaded region here, this shaded region. So any point of production below the ISO cost in the practical world, it's more like, my battery is running low. So in the real world, let me just save the recording before we get shocked.